In this screencast, we'll take a look at how to convert words into both a P&ID and a block diagram. So we'll do this by using the somewhat lengthy example provided on the screen, where we have a stirred tank heater which we're trying to use to heat up a process stream. Our control objective is to control the process stream's temperature by adjusting the flow rate of steam which is coming in through a coil for the tank. There is no direct contact between the process stream and the steam. Additionally, we have an issue where the flow rate of the process stream we have no control over and can vary. Additional information includes the energy balances that relate our variables together. So we have two energy balances. The first for the coils, which shows the steam temperature as a function of the tank temperature and the steam flow rate. And then we have a second one for the tank, which has a relationship of the tank temperature as a function of the steam temperature and the flow rate of the process stream. So what we're going to do here is develop the P&ID and block diagram. So to start with, we'll have our tank here. We know we have a stream coming in, which is the process flow rate, which will be a flow rate to F, and F coming out, but we know that it can vary, so it can be a function of time. Based on the fact that we have not been given a mass balance, we can assume that these two flow rates will always be identical. Additionally, the temperature of the fluid inside the tank will be T, which also can vary as a function of time. We'll assume no energy losses, something that you can see by the definition provided for the tank. We can assume the outlet temperature is the tank temperature because there is no additional variable for an outlet tank temperature. The next part we have to add is the steam. So the steam will come in via a coil, and we'll have Fs representing the steam flow rate here, and Fs going out. We're assuming there is no accumulation of steam in the coil. To develop the control scheme for this, what we're trying to control is the temperature of the process stream. In this case, it doesn't exactly matter whether or not we choose to put the temperature sensor in the tank or on the outlet. The difference will be quite negligible because the temperature is the same in both. But for the sake of this, we will put our temperature sensor inside the tank and measure that temperature. And we know that our controlled variable, we're doing this by controlling the flow rate of steam, so we'll need a valve here for the steam, or some sort of final control element. So then we will add our controller and connect the controller to the valve. Here is our P&ID. Now, before we go into the block diagram, it'll be important to look at our variables that we have defined in the energy balances and see what they're all about. So give us some idea of how these are going to fit into developing a block diagram. So we know that the variable that we're trying to control here is the temperature, T. So this tells us that T will be our controlled variable. We are attempting to control this via adjusting the steam flow rate. So therefore, this will be our manipulated variable. The flow rate of the process stream is something that we can't control and is allowed to vary. So therefore, this represents a potential disturbance to the process. So therefore, this represents a disturbance variable. And T prime S is some sort of intermediate variable which will be changed based on these energy balances. However, it is something that we cannot directly control, and it is not something that we are trying to control. By looking at the energy balances, you can get the feel that the steam will be related to our respective flow rates. Just take a quick check back and forth between our variables in our equations and our variables in our P&ID. We see that 3 of the 4 variables are present. However, the steam temperature was omitted. So for completion, we can put the steam temperature into our variable here. And in this case, the steam temperature of interest will be the one that is coming out of the coil. So now, as we move along to the block diagram, we can begin to draw this by starting actually at the end. We know that the variable that we're trying to control here is the temperature of the tank, which is also the outlet temperature. So in order for this control system to work, what's going to happen is the temperature has to be sensed and transmitted by the temperature sensor shown here in the diagram. So therefore, this will represent the sensor transmitter block. So what will come into this is a temperature in degrees Celsius or some other units, and what will come out is some units representation of this in transmitter output or in milliamps so that the controller can understand it. in order for the controller to make a decision, it has to compare the actual value to the set point. So we're going to have our set point temperature here, and then we're going to need a gain in order to convert that into percent transmitter output. So again, here the units will be percent transmitter output. Here, for the set point of the temperature, units will be in degrees Celsius. So we need some way to convert units. So that's what the KM block does. From there, the controller will take the signal. So again, we look at the diagram here. The controller will take the signal from the sensor and compare it to the set point, which is something already programmed into the controller. And then following that from there, the controller will then send its signal to the valve. So if we go back to the block diagram, GC will go to GV. So to show where we're going now is if we look at this, the summing point here, the difference between these two is an error in percent transmitter output. So this is the error. What will then be reported to the controller, what will come out of the controller is some percent controller output. And that percent controller output corresponds to how open the valve should be, 25% open, 60% open, etc. And that openness of the valve corresponds to the flow rate of steam. So therefore, we have the first of our variables present, which is the flow rate of steam. But now the question is how do I get from the flow rate of steam to the temperature of the tank? And we can see that the transfer function for the flow rate of steam and the temperature of steam are related by transfer function G2. So what will come out of G2 is the steam temperature. However, that is incomplete because the temperature of the steam is dictated both by a transfer function related to the steam flow rate and a transfer function that's related to the controlled variable. So what this means here is we see this addition here, this plus. So that means that in order to get TS, we're actually going to need a summing point. We'll have two positives, and we're going to need to sum the multiplication of G1 times T. T is already our controlled value. We've already put it in the diagram. So we can draw a branch off of that and then add a G1 block in order to carry out the multiplication. So if we look at what we have represented as TS, it is G1 times T plus G2 times Fs, which is what the relationship we have here in the coil. So finally, to relate TS to T, we need to have the relationship between the variables using the tank equation, and that can be done in a very similar fashion where we'll have G3 times TS, but we'll once again need a summing point with another variable, in this case our disturbance variable, which is F, and then that variable corresponds to a transfer function of G4, and then we connect the summing point there. So this here represents our block diagram for the process. So through this screencast, it's hopefully possible for you to be able to condense the information provided in a somewhat lengthy problem statement and turn it into information that could be relevant from a control standpoint, both developing a block diagram and developing a P&ID.